Okay, so what we are going to now go into is the formation of carbocations and the reactions that you get out of them. And before we can launch into carbocation formation, I wanted to briefly cover leaving group ability. And this is a chart that essentially shows um, leaving group capacity, and it really does basically lay it out in the context of how strong the pKa of the conjugate acid is. So if we look at the pKa of hydroiodic acid, for instance, that is just an unbelievably acidic compound. And so the conjugate base is, of course, not basic in any meaningful way whatsoever. You can see conjugate base, I minus, is essentially not a base. And so it is one of the best leaving groups. Paradoxically, one of the best nucleophiles, but also one of the best leaving groups. And this goes again to the fact that nucleophilicity and basicity are two different components, all right? So as a general rule, what we're going to say is that the worse base it is, the better leaving group it is. And leave it at that, all right? So you can see that as you move down this chart, you end up with worse leaving groups to the point where you really do not see alkanes depart. Hydrides do not come off. That's H minus. NH2 minus doesn't come off. And you know, in this class, these things are not stuff you will see depart either. Hydroxide and methoxide. We're essentially going to say that those are not leaving groups. Um, Organic chemistry is a gray area sometimes, and so they can be leaving groups, but they're just so bad at it. Why bother? Really getting into detail in this sophomore introduction to organic chemistry. The one thing I will point out is fluoride F minus is just an anomaly, and I did cover that in the previous lecture. F minus is not a leaving group, and so we're going to just leave it at that. You don't kick off fluoride. And then things that you do expect to kick off are things that are highly resonance stabilized. Halogens, water is an excellent leaving group. And in many cases, so is acetate and NH3. So those kicking off those things is either a fairly weak base. I mean, it's a base, but it's not very strong. And ammonia, and this is about the strongest base you're going to end up kicking off is ammonia. And you won't see that happen too often either. Now, why do I bring this up? All right, well, it's important to appreciate how carbocations form, and they form pretty much spontaneously. And so we had said that a tertiary carbon, or at least we kind of insinuated that tertiary carbons form carbocations really easily. And so if you have something that looks like this is very clearly a tertiary carbocation, and that's going to draw an iodine right there. And you have an iodide, which we know is a wonderful leaving group. What you will have is an equilibrium between these two structures and the formation of a carbocation. And that carbocation is going to be, in fact, let me draw this very specifically because as I had said, carbocations form as sp2 hybridized structures. And so what you have is something that looks like that, all right? And those are positively charged. We'll just make only one positive charge so it's very clear. And then we also have I minus that has come off. So we haven't lost any charges. There's still a plus charge here, and there's still a minus charge here. And if you add them up, they're neutral, just like what we started with. So that's good to keep our math together. But there is a discrete equilibrium here, all right? Now, you can imagine when this compound is like this, when it's in this equilibrium form, right? These aren't resonance structures. This is an equilibrium, so this is a genuine thing that forms. Essentially, you've got a naked carbocation, so any nucleophile that wants to come along and attack, even if it's uncharged, let's say this is, in fact, let's just give this a proper nucleophile. We'll call it an amine. All right, this can come in and attack right here. And what's important is that this is incredibly fast. All right, this equilibrium is slow, but this attack is going to be fast because you have an open p orbital that anything can come in and attack. If it's got a lone pair or a negative charge, it's got a full octet, but it's still too electron rich and it wants to dump some of that stuff. That is going to be a very fast process, at least relative to the formation of the carbocation. And then what you end up with is, well, either, I don't want to be too specific on the stereochemistry because, of course, this can also attack up here. There's really no difference in those two p orbitals. They're both the same orbital. But what you end up with is a carbon with CH3, CH3, CH3. And there's no stereochemistry here because it's not a stereochemically selective reaction. And then you end up with NH3+. All right? And then, you know, we still haven't actually created a positive charge out of nothing. There's still that negative charge there on that iodine. That iodine, I guess, could go pull off a hydrogen there if it so wanted. But this is fundamentally what an SN1 reaction is, okay? So an SN1 reaction, as distinct from an SN2 reaction, means that what you end up getting, what ends up happening is there's a formation of a carbocation, right? So there's a formation of a carbocation, and then the nucleophile attacks. So let's really quickly go back over and see why that happens from an energetic landscape. So in an energetic landscape, what we had said in the SN2 type reaction is you have a starting material and a product, and we're going to assume our product is lower in energy. And in an SN2 reaction, you have something where you have a transition state, right? And so if what we drew up there was usually it's CH4 or CH3, sorry, let's get this. All right, it's some sort of CH3 iodide, all right, and then there's a nucleophile. And in an SN2, I made it quite clear that this has to be a very small substituent. So it really can't be any substituents. And it attacks, and then you go up into some sort of transition state, and that carbon has Texas carbon. It's got 5 substituents coming off of it. A nucleophile is approaching, and an iodine is leaving, right? And the product is your CH3 nuke, okay? Now, kinetically, all right, and again, kinetically is this part of the reaction, or essentially the activation energy. Between here and here, the energy of activation. Kinetically, what is important is substituent size. Now, there are other important factors, but the big important factor in determining how fast this reaction will go is how large the things are on this carbon. I've got 3 hydrogens here, but let's say I made them bigger, right? And everything comes down to being able to form this really crowded 5-membered transition state. So if I made those bigger, say I wanted to replace a hydrogen or 2 hydrogens with a methyl, that would be much slower. All right, let me use a different color. That would be much slower. So if I wanted to make the transition state bigger, by taking a product instead that is CH3 2 CHI, all right? And what does that look like? Remember, that's CH3 CH3 HI. So now it has 2 bulky substituents coming off of it. The transition state now looks something like this. We've got CH, H, H, we got something coming out towards you, and that's got C, H, H, H. And then it still has a little H going back here. Okay, and we've got our leaving group coming off. And all right, how am I going to draw that? I'm going to just have to stretch that back there. That's our iodine leaving, and then we've got the nucleophile. That doesn't seem, that's coming in there. And you can see that this transition state's a lot bigger. It is a lot harder to form, and it is consequently what you would call much higher in energy. That means that this reaction is probably not going to happen. Essentially, you require so much energy in order to get up here. Your new energy of activation is going to go from here all the way up here. So that's a huge amount of energy of activation. And what that essentially tells you is at some point, you just can't pump enough energy into a solution. Something else is going to happen. And I already said that this iodine is in an equilibrium between carbocations. So instead of actually trying to undergo this chemistry, you end up getting your product. You end up getting the final product down here. And it's roughly the same energy as if you do, in fact, isolate. It's not like this reaction doesn't proceed at all. It just doesn't proceed through this mechanism. Because you see, the amount of energy necessary to form that transition state just doesn't exist. So instead it undergoes a slightly different reaction path that we call SN1. And the SN1 reaction path, instead of trying to get everything done at once, undergoes sort of in this stepwise process, where instead of having two things coming together, bonking each other at the same time, well, you're just going to start out with one, just one, instead of two, right? Instead of starting off with two things and trying to smash them together, you're just going to start off with one, and that is our, let's draw this again. CH3, 2, CHI. And the first transition state is actually going to be this bond getting really long. This bond just getting so long it's about to snap. So effectively what it is what is that? There we go. Is this, except that bond's just starting to get long. It's a transition state. We can say that this just really it's starting to break. All right, and it goes into actually a stable intermediate. And that stable intermediate is the carbocation. Plus. All right, so that intermediate's actually stable. And the second step of the reaction is actually very fast. As I said, it was very fast. There's hardly any energy necessary to go into it at all. And that is the attack by the nucleophile. All right, and so what we end up drawing here as our second intermediate is this. Except instead of a plus charge, what we're going to draw is this carbocation now forming to our nucleophile. So this is now our intermediate. It's just a really long bond, a fictionally long bond, if you will. That's just what our transition state structure looks like for that part of the reaction. Let's try to just get this down here just a skosh more. All right, and then we end up with our product. Nucleophile attached to the starting material. All right. Just close that out. There we go. So why is this called an SN1? Well, it's SN1 because it only involves this. That is the only thing that matters in this entire energy diagram. I mean, obviously you need the nucleophile in order to make the product, but here's the thing with activation energies, all right? Activation energy is the amount of energy necessary to go from here to the tallest bump, all right? So That's it. Presumably, if you have enough energy to go here, you have enough energy to go here as well, right? There is an activation energy, and we can even call this, we can even give it another name if we want. We'll call it activation energy 2. But you're doing the reaction, you already have so much energy over here, it doesn't make any difference what that is because you already have enough energy to get over this hump, so who cares? So what you end up with is you have something called the rate limiting step, all right? So the rate limiting step essentially is whatever the highest bump is, whatever the highest activation energy. No other activation energies actually make any difference because they're all going to be lower. So as a consequence, in SN1, the only thing that matters is this hump. So kinetically, what SN1 says is the rate of your reaction, and this is essentially our law, the rate law for SN1, and that's actually what it's called, the rate law. Rate law is rate times lowercase k, whatever that is, times our starting material, the thing that's going to form the carbocation, CH3, 2, CHI. The nucleophile doesn't matter because the nucleophile only comes in after the rate limiting step. So it doesn't make any difference what it does. It essentially isn't even obvious when you do the experiment. Because the thing about rate limiting steps is, and when you do this experiment, say, you just monitor the loss of this, all right? All you're going to see is this. So what's another way of saying that? So if you have a rate law that looks like that, and I told you, in an SN1 reaction, if I added more nucleophile, will it go faster? Hopefully you say no, because the rate has no nucleophile term in it. All right, but if we go back up to SN2, if we look at what is in the rate limiting step, and there's only one transition state, so that tells us exactly what's in the rate limiting step. The rate limiting step and the rate law for an SN2 reaction is always going to have both starting materials. So that's going to be CH3I and the nucleophile. So what exactly does this rate law mean here in the context of SN2? If I increase the concentration of electrophile or if I increase the concentration of the nucleophile, my overall rate goes up. I can increase either and my rate will go faster. In the context of an SN1 reaction, the only thing that's going to affect the rate of my reaction is if I add more electrophile. I can add as much nucleophile as I want, but like I said, because it's on the other side of my rate limiting step, it doesn't matter.